Hi students, welcome to Suneel Engineering Academy. I am Sunil Kumar Bandaru. Students, in the Transformers, we have completed 3 sessions. It is the fourth one. All these sessions are useful for all your competitive examination. The students who are searching for the course in which you will get only the important points. Okay. So let me check up to which we have completed. So transformer basics we have completed, constructional details, transformer winding, types of transformer and all the parts. Okay, characteristics, EMF equation and those observations. Now we are going to discuss the operation of transformer. Okay, in the first of all, we are going to take no load operation. Okay, operation of a transformer with the iron losses. At no load only we have the iron losses. Okay, so that's why we have to take the operation of transformer with the iron losses. Okay, so especially at no load we have only the losses, iron losses. At no load we may have the losses are nothing but, you can say, iron losses. Okay, so for example, no load in the sense load is not at all connected. Here I am taking the rough diagram of transformer. Okay, so this is the one winding, this is the another winding. Let us take number of turns n1, n2. I am going to give the supply to this winding, so it will become a primary. Okay, voltage. If you give the voltage, then current is flowing. Okay, current is flowing, and here the flux is produced. That flux is transferred to the secondary. Okay, here EMF is produced, but here load is not at all connected. Okay, so here we have the EMF E2. Here EMF E1 we have. Okay, so flux is flowing. Flux is flowing. So no load, let us take the no load current as I naught. Let us take the no load current is I naught. This I naught is sum of working component of current plus magnetizing component of the current. Here generally you can say it is the vector sum. What is this working component of the current? IW is the working component of current. Component of current. Okay, I mu is considered as magnetizing component of current. Okay, so this I mu is the responsible for magnetic losses or is responsible for to produce the flux. Okay, it is responsible for to produce the flux. And IW it is supply, it will gives the power supply to the iron losses. Power supply to the iron losses. Let us take some differences between this IW and I mu. This IW and I mu. Taking I mu here, here IW. Okay, so I mu is nothing but magnetizing component of the current. So here you can say it is the reactive component. Reactive component of current. Here it is active component of the current. Active component of current. Okay, so that means due to it serves the iron losses. It serves the iron losses means you can say what full losses are in the power. So what full component. Okay, reactive in the sense what less component. Okay, so we can simply understand by using the network analysis. IW is nothing but it is to meet the resistive losses. Okay, it is to produce the magnetic flux. That means it is the inductor. Let us take a pure inductor. Let us take a inductor. If you send some current through the inductor never absorbs any amount of power, correct? Okay, so the pure inductor may not absorb any power. But this inductor is made with some copper, so it has some resistance. Due to that resistance, we are getting some losses, correct? So whenever the current is flowing through this inductor, due to the resistance, we may have some losses. That corresponding current is working component, and here inductor is there now. Whenever the current flowing through the inductor, there is a flux is produced. To produce this flux, we require the current, that is the magnetizing current. All of you getting? That is the magnetizing current. Okay, so due to this current, we may have the losses. Due to this current, we may get the flux. Okay, we may get the flux. So that is the difference. Okay, so here this is a resistive component in the sense it is in phase with the voltage. Okay, it is always in phase with the voltage, with the applied voltage. Okay, it is purely inductive component. Inductor in the sense whenever the current flowing through that inductor always lags. Okay, so you can say it is always current. This current is always quadrature, that is lags with respect to voltage. Okay, with respect to voltage. And here this I mu is just for example, total I naught is considered as 5 to 6%, 5 to 6% of full load current. Okay, in this case I mu is more, really nearly 4 to 5%. Okay, remaining 1 to 2% is to meet the losses. So that is IW. Okay, so it is very less, it is very more. Okay, so we can represent this I mu in a simple manner. In inductor, the current flowing through this inductor is I mu. So here the I mu is to get the magnetic flux. So it is a magnetizing component and it has purely that is inductive, or you can say reactive. Okay, so that means I mu is equal to, we can take I naught sin pi naught. Okay, I naught is the no load current, and how to represent the working component? Resistive. Okay, resistive. So that is R naught. So here working component of the current. So IW is equal to I naught cos pi naught. I naught cos pi naught. So if you can take the sum, I naught is equal to, or you can take I naught is equal to I mu plus IW. If you take square on it, or if you take a square, I naught square is equal to I mu square plus IW square. Okay, IW square. So I naught is equal to root of I mu square plus IW square. That is I naught square sin square pi naught plus I naught square cos square pi naught. So sin square theta plus cos square theta is equal to 1 na. So I naught is equal to root of I naught square plus sorry again you will get the same thing na. Okay, sorry. So can take like that. Okay. I naught square is equal to I mu square plus IW square. Okay, so I naught is equal to root of I mu square plus IW square. Okay, so this is the thing you will get. This is the no load current. No load current of transformer. No load current of transformer. Very, very important. Here I mu is quadrature with respect to the voltage or lags 90 degrees with respect to the voltage. Okay, IW is in phase with the voltage. So let us take all these in the diagrammatic manner. Okay, diagram manner. So in no load condition. Okay, so let us take any reference. I am taking the flux pi naught is the reference. Okay, flux pi naught is the reference. Here voltage always leading with respect to 90 degrees. Wherever there is a voltage, IW is the in phase with voltage na. IW is in phase with voltage. Okay, and what about the I mu? I mu is the quadrature, that is lags 90 degrees. So I mu is lags 90 degrees with respect to the voltage. Here I mu. Okay, so if you take the vector sum of these two, this is the vector sum, that is I naught. That is the I naught. So the angle between V1 and I naught is pi naught. So pi naught value is very high, nearly 60 to 70. Okay, nearly 70 degrees. 70 degrees. Okay, nearly 70 degrees. And we know very well what about the E1 and E2. So there is the angle between voltage and EMF is 180 degrees. We have already discussed in the class first. Okay. So from this one, we can say that under no load, transformer behaves as inductive reactor with power factor is approximately 0.2 lag. Correct? So here pi naught is nearly 70 to 75. So cos 70 to 75. So we know very well cos 60 is 1 by 2. Cos 90 is equal to 0. Okay. So the between 0 and 0.5. So that means maybe 0.2 or 0.25. Okay. Very, very less power factor. So the very important question here, under no load, the power factor is very less, 0.2 lagging or 0.25. Okay, so note down here, pi naught is the no load phase angle of transformer and the range is 70 to 75 degrees. Okay, 70 to 75 degrees. And in the same way, so cos pi naught is the no load power factor. No load power factor. The range is 0.2 to 0.25 lag. Okay, 0.25 lag. So because here, and one more thing, if you can consider this is the IW, this much of I mu. So what is the relation between IW and I mu? I mu is very much greater than IW. Very much greater than IW. So that's why if you can consider I naught is 5 to 6% of full load, in this it will be divided as it is 4 to 5%. It is 1 to 2%. Okay, 1 to 2%. So IW is less, IMU is more. So it is a very, very important thing. IMU is very much greater than IW. Okay, because of this, I naught, sorry, because of this, the power factor cos pi naught is very less, very less. Okay, higher the magnetizing current means it is the inductive nature. Inductive nature means power factor is very less. That is a simple idea. Okay, no need of any in detail explanation. Okay, clear? Okay, so now let us take equivalent circuit of transformer under no load condition. Equivalent circuit of transformer under no load condition. Okay, equivalent circuit of transformer under no load condition. Okay, so in this it is a very simple representation. Here if we have the transformer and these are the windings. Okay, here we can represent these two lines. What is the representation of these two lines? What is the representation of these two lines? Okay, so please give in the comment section. In the next session I will give the idea. Okay, what is that representation of two lines? Okay, let me check how many students will give the answer. It is N1 N2. Okay, so here if you apply the voltage here, then current is flowing. Okay, so if there is no load is connected, then only we have the no load current is flowing. That will be divided as two parts. One is like a resistive, the current which is flowing through the, to meet the resistive losses, to meet the magnetization. Okay, so this is, let us consider as R naught. This is, let us consider as X naught. The current flowing through this is IW. This is I mu. Okay, this is I mu. So I naught is the vector sum of IW and I mu. Okay, so it is nothing but you can say, you can also call as shunt branch parameters. Shunt branch parameters. Okay, here we have the no load voltage E2. This is the equivalent circuit representation. Okay, so here I naught is equal to vector sum of IW plus I mu. Okay, so here if you want R naught. Okay, so across this we have the voltage V1 by the corresponding current IW. So you can get R naught. If you want to get x naught, across this we have the voltage V1, the current flowing through this is I mu. So like that you can calculate R naught and x naught. Okay, you can calculate R naught and x naught. Let us take the same vector diagram of lagging power factor. Whenever we have connected the load on load, if it is a lagging power factor, if it is a lagging power factor. Okay, so all of you try to understand. I am taking reference as pi. Okay, so our voltage leads. First of all, you apply the voltage. After that one only the current is flowing, then flux is producing. Okay, so the current flowing to magnetize that is magnetizing current. To meet the iron losses, we have the working component of the current. After the flux, we have the EMF. That is the EMF E1 and E2 both are in phase. Okay, EMF E2 is always almost equal to V2. So V1 is equal to minus E1 we can consider. Okay, now what they have given lagging power factor. Lagging power factor is nothing but current is lag. So now current is lag or load is lag. So load current in the sense you can say I2 na. Load current, the current which is flowing through this load is nothing but you can say I2. Okay, the angle between V2 and I2 is, let us take pi 2. Okay, pi 2. If you extend this I2 in this just wait. If you extend this I2 in this, you will get like this. Okay, so let us take this one as I1 dash. I2 is extending in other side, then you can say that is I1 dash. I1 dash is equal to K times of the I2. K times of the I2. Okay. Now this is the I mu, this is the IW. Then what is the I naught, guys? I naught. I naught is the vector sum of these two, correct? So this is the I naught. Okay. Now vector sum of these two. Vector sum of these two, that is I1 plus I naught. So vector sum of these two, I naught plus I1 dash. Okay, I naught plus I1 dash. This is nothing but you can say I1 current. This is nothing but you can say I1 current. So what is the angle between V1 and I1? Let us take is a pi 1. So pi 1 is angle between V1 and I1. If anyone not getting, just backward, okay, go to backward and watch again. Okay, so you can easily get. Okay, I have given full step by step manner. First of all, I have drawn pi and voltage is leading, or you can draw voltage. Okay, if you apply the voltage, flux is produces. After the flux is linked with coil, then EMF is produces. Just I am taking current is lagging. I am extending in another side. I am taking as the I1 dash, that is equal to K into I2. Okay, so vector sum of this I naught and I naught and I1 dash is nothing but you can say I1. You can say I1. Okay, now this is the angle between V1 and I1. Okay, V1 and I1, and the angle between, let us take uh, this is the pi 2, this is the pi 1. Okay, yes, from these two, pi 2 is the angle between V2 and I2. From these two, what you can get understanding, guys? Pi 1 is more, na? Pi 1 is more, as pi 1 is more than pi 2. That means, what about that cos pi 1 is less than cos pi 2 now? We know very well. Cos 0 is equal to 1. Cos 90 is equal to 0. Okay. So that means reversal, inversely proportional. So here also, as the angle is more, power factor cos pi is less. As the angle is less, power factor is more. Okay. From these two, what we can say? So cos pi 1 is the primary power factor is less than cos pi 2 is the load power factor. Load power factor. Okay. Load power factor. So here in case of lagging power factor, finally what we got? Primary power factor is less than that of the load power factor. Primary power factor is less than that of the load power factor. Okay. And also we got one more relation. I1 is equal to I0 plus I1 dash. This is also vector sum. This is also vector sum. Okay. Vector sum. Okay, all of you clear? Let us take same this in a leading power factor. Listen carefully. If you listen carefully, then no need to read again or no need to practice. Leading power factor. Leading power factor. Okay. So first of all, you have you take the reference as pi, or you can take if you apply the voltage V1. After some time you are getting the flux. This is the phi 1. Okay. And after that you will get the EMF E2, E1. Okay. That is nothing but you can say E2 is nothing but you can say V2. Here leading power factor. Current leads. Current lead in the sense this is not your current is leading phi 2. Your current is leading. Okay. You have the leading current that is phi 2. I am extending this current in another way. Okay. So if I am extending this in another way, you will get I1 dash that is equal to K into I2. Okay. Here you have I mu. Take this one as with the blue color. I mu IW. Vector sum of these two is the I naught. This is the no load current. I naught. Okay. Now coming to vector sum of these two. Vector sum of these two. I1 dash plus I naught. So what is the thing you will get? Let us take purple color. Okay, this is the one I1. Now the angle between these two is phi 1. From that one, what you can understand? Phi 1 is less than phi 2. Phi 2 is more. Phi 1 is less. Okay, so that means cos phi 1 is greater than cos phi 2. Okay, so that means primary power factor here, primary power factor is greater than load power factor. Primary power factor is greater than the load power factor. So note down all this point. Okay. So note down the point when power factor of leading load on secondary side power factor of leading load on secondary side increases, then primary power factor is decreases. Okay, that means what we can say, as cos pi 2 is increases, as cos pi 2 is increases, cos pi 1 is decreases, cos pi 1 is decreases. Okay, when this cos pi 2 is increases, whenever the pi 2 is decreases, when cos pi 1 increases, when pi 1 increases. Okay, when it will be happen, if you decrease the pi 2, if you decrease the pi 2, that means if the I2 is coming near to this, then what will happen? If it is coming near to this, then you will get, this will be shifted like this. If it is shifted like this, then this will be shifted. If this is shifted, then pi 1 is increases. So pi 1 is increases. As pi 1 increases, cos pi 1 is decreases. Okay. So like that. Okay. All of you getting my point? Simple, guys. Here what I'm saying is, if you increase, if you move this curve like this, if you move this vector towards to the V2 side, that means you are decreasing the pi 2. If you decreasing the pi 2, then what will happen? This one becomes like this. So if it is becomes like this, then it will goes to like this. So then this is your new one. So your pi 1 is increases, correct? So as pi 2 decreases, pi 1 is increases. That is the point only. Okay, if you know this one, power factor is reverse. Power factor is reverse. Okay, so let us take one question on this, then you will get easy understanding. Okay, so let us take one question on this, then you will get understand. If the load power factor of transformer is, if the load power factor of transformer is 0.8 lakh, then its primary power factor is dash. They will give the question like this. Option A 0.9 power factor, option B 0.8 power factor, option C 0.7 power factor, option D unity power factor. Then what is the answer, guys? Then what is the answer? In case of, they are asking lagging power factor. Okay, if the load power factor of the transformer is 0.8 lag, then what about its primary power factor? In case of lagging case, what you got? Primary power factor is less than that of the load power factor, correct? So note, take that point. In case of lagging, you got that primary power factor. Okay, primary power factor is less than that of load power factor. In case of leading, what you got? Primary is greater than load power factor. In case of leading, you got, these are the two important points. For these two important points, I have given all the data is greater than load power factor. So in this case, in case of lagging case, primary power factor is less than load power factor. Load power factor given 0.8. So less than 0.8. How many options we have? Only one option. So C is the answer. C is the answer. Okay. In case of leading, it may be greater than 0.8. Then you have two options. Okay, you have two options. But if they have want to give that in a leading power factor, they may not give as UPF. Okay, maybe they will use 0.9 power factor only. Okay, so 0. So in this case, primary power factor is greater than 0.8. Okay, so in this way we can easily give the answers. Okay, now let us take a very important point, that is nothing but effect of winding resistance if you transfer from primary to secondary or secondary to primary. Okay, that is a very important one. So let us take that one. Okay, just wait. Effect of resistance. Effect of resistance, that is nothing but winding resistance on the operation of transformer. Let us take a simple transformer diagram. Okay, core of the transformer, we have the two windings, one winding, another winding. Okay, so if you have more turns, then you can say that is the HV. If you have less turns, that is you can say LV. Okay, so if you connect this side as supply, then it will becomes primary. So I have given the voltage here, then current I1 is flowing. Okay, so this winding having some resistance, let us take R1, and this is connected to load ZL. Okay, so this is nothing what you can say R2. Here EMF is produced, here EMF is produced E2, and across this we have the voltage V2. Across this we have the voltage V2. Okay, so here you can say R1 is the primary side resistance. Okay, R2 is the secondary resistance. Okay, all of you clear up to this? So due to resistance, what will happen? We can say due to resistance, we may have voltage drop, IR drop. So that is nothing we can get voltage drop. And what about another? We may also get I square R losses. I square R losses. So if it is an ideal transformer, we can consider R1 is equal to R2 is equal to 0. Okay, no winding resistances. But in practical, we don't have that type of the windings. Okay, always windings have some resistances. Okay, now the question is transfer of resistance from secondary to primary or primary to secondary. Okay, why we need to transfer? For easy calculations, for easy calculation. Okay, why? Because if you transfer resistance to secondary to primary or primary to secondary, it will become a simple circuit, simple electrical circuit. You can easily get the analysis. Okay, so for that way we can we have to transfer the resistance. First of all, I am transfer of resistance from secondary to primary, secondary side to primary side. Okay, transfer of resistance from secondary to primary. Okay, so I am taking the diagram here. Here I have the resistance R1. Okay, after that we have the transformer is like this. Okay, here we have our R2, but I am transferring this R2 to this side. Okay, R2 to primary side. So I am transferring this R2 to primary side. So whenever I am transferring this R2 to primary side, to represent this R2 in the primary, this is the R2, but this is representing in the primary side now, one side. So take this one as dash, R2 dash. Okay, so it is the resistance of secondary side, but it is converted to primary. So for that primary, I am taking the representation as R2 dash. Okay, all of you clear now? R2 dash. So if you transfer the resistance from primary to secondary or secondary to primary, whatever it may be, here we have the current is I1. So the losses are same now. Due to resistance, we may get the losses. Those are same. If it is connected in the primary or secondary, whatever it may be, the losses are same. Correct? So the losses I am considering, if it is in the R2 manner, if it is in the R2 manner, there is current I2. So then what about the losses here? I2 square R2 is the losses here. Here, if you connect that into a primary, so what are the losses? You will get I1 square R2 dash. Correct? Okay. If you connect the resistance here or here, whatever it may be, you may get the losses are same. If the I1 current is flowing, I1 square R2 dash is the loss. Okay. If the I2 current is flowing, I2 square R2 is the loss. So losses are same on both sides. So you will get I2 square R2 is equal to I1 square R2 dash. All of you clear or not? A very simple case. If you place a resistance here or here, due to resistance, we may get the losses. Correct? For example, here it is the R2, it is the I2. What is the losses here? I2 square R2. Correct? If you have here that R2 is coming to the primary side, it will become R2 dash. Here the current is flowing I1. Then what is the losses? I1 square R2 dash. Both are same. Correct? Okay. So same resistance na. Here it is the 5 means here it is also 5 only. Losses are same. Okay. So if the losses are same, I am taking here like this. From this, I want this R2 dash na. R2 dash is equal to send this I1 square to this side. Then you will get I2 square by I1 square into R2. So I2 by I1. I2 by I1 is nothing but 1 by K. 1 by K na. So that is R2 into 1 by K square or 1 by K square into R2 for your easy understanding. As we know, K is equal to I1 by I2. So that is I2 by I1 means 1 by K square into R2. So from this, finally what we can get idea? R2 dash is equal to R2 by K square. So this is the final thing we need to remember. Okay. So no need to draw all these in the examination. We require secondary to primary R2 dash. It is the secondary resistance, but you converted into primary side. One indication means converted into primary side. Then R2 dash is equal to R2 by K square. R2 dash is equal to R2 by K square. If you transfer the resistance from primary to secondary, then what will happen? Okay. primary to secondary. Transfer of resistance from primary to secondary side. Let us take a diagram. Just for understanding, I am drawing all this diagram. Okay. Other no need in the examinations. Okay. Here we have the transformer, and this is the core. Okay. So here we have the R2, R1. Okay. Now I am transferring this R1 to this side. Okay. So this is the R1, correct? R1, but okay, but it is belongs to secondary side. We are transferring, so R1 to R1 dash. Okay, for transferring you can say it is a dash, so R1 dash. Okay, so this R1 from primary to secondary. Okay, so this R1 indication is the primary winding. It is transfer from one side to another side, means we represent as dash. We represent as dash. So here I1 current is flowing, here I2 current is flowing. So whatever it may be, due to that resistance, we may get the losses. The losses in the primary side, you can say I1 square R1 is equal to, here due to I2 current, we are getting the losses I2 square into R1 dash. R1 dash. So we require R1 dash now. So send this I2 square that side. R1 dash is equal to I1 square by I2 square into R1. So I1 by I2 is the K now. So then you will get K square into R1. So this is the relation. Primary to secondary, you have multiplication of K square. And secondary to primary, we have division of K square. Okay, division of K square. Sir, why we require all this concept? We no need of any concept. We want just tricks to remember. Okay, to avoid the confusion. All of you want the tricks? I know that you are always waiting for tricks. Okay, no need of concept. So let us take a small trick. Okay, let us take a small trick. What is that small trick? First of all, let us take secondary to primary. What do you get? Secondary to primary. Secondary to primary. You got division. So secondary to primary, you got division. So SPD. SPD in the sense, you can make it this one as a simple trick. SP dosa. SP dosa. Special dosha. Dosha is your favorite. If anyone having dosha as your favorite, give in the comment section which dosha is your favorite. Okay, in dosa you have so many varieties now. Plain dosa, karam dosa, masala dosa, upma dosa, onion dosa, paneer dosa. Okay, so SPD, all of you clear? SPD. So secondary to primary, it will be a division. So secondary to primary, it is a division. Okay, secondary to primary, correct? It is a secondary resistance. Secondary to primary, it is a division. So that is division in the sense by K square, R2 by K square. Okay, so R2 by K square. And the second one, if you can consider primary to secondary. Primary to secondary. What you get? Multiplication. M. Okay. So you know very well plug setting multiplier. Plug setting multiplier. PSM. In the power systems, we have plug setting multiplier. PSM. Primary to secondary is the primary resistance. converted to secondary, then it will be a multiplication. K square of R1. K square of R1. So like that simply you can remember. Okay, all of you got the trick. If you like the trick, give in the comment section. Sir, your tricks are very good. Okay, try to give some comments here, some positive comments. Then only I will get the motivation. Huh? You are not at all giving any money, na. At least give some comments. Then I will get some motivation. Oh, so and so students are watching my class. So and so students are watching my class, and then after that they got into selected for RRB JEE or SSC JEE. I feel proud. Okay, you know one thing, in 2021, 2022 and 2019 RRB JEE, 2020, 21, 22 SSC JEE. So many of my students got selected. All India second rank in SSC JEE 2021 is our student only. Okay, so at the time I have given classes in Unacademy Plus. If you want those classes, you need to pay a lot of money. But now all the classes are free. Okay, all of you clear? Clear the tricks. Nowhere you will get this type of tricks. Okay, and from many days I'm saying the same thing. No need to follow my trick. You can make your own trick whenever you are in the confusion. Okay, not only in this subject, in any subject, if you are in the confusing mode, try to make a small trick, then it will avoid the confusion. You can easily get the answer within seconds. Okay, yes. Now after this we have to take a summarize of all these. Okay, so if you can consider total resistance, total resistance of transformer on primary side. Total resistance is considered as R01. Primary side in the sense R01. This is the sum of R1 plus and secondary to primary transferring resistance. Okay. So here R1, this R1, and you are transferring R2 here. So R1 plus R2 dash. Okay, R1 plus R2 dash. And the same way, total resistance of transformer on secondary side R02, that is R2 plus R1 dash. Okay, and total copper losses. Total copper losses on primary side. So what is the current of the primary side? I1 square, and total resistance R01. Let us take same total copper losses on secondary side. Secondary side we have the current is I2 square and the total resistance R02. Total resistance are R02. So total copper losses on both sides. So I1 square R01 plus I2 square R02. Okay. Sorry. Copper losses on primary side is equal to secondary side na. So that means I1 square R1 plus I1 square, sorry, here I have given some mistake, I think. Okay, so I1 square R1 plus I2 square R2. Okay, so total copper loss is equal to the current flowing in the primary side, that is I1 square R1 plus I2 square R2. Or we know the copper losses on the primary side is equal to secondary side. Okay, so that means here you can say that is equal to, let us take I1 square R01 or I2 square R02. Okay, so from this one what you can say, The copper losses on either of the side is equal. Either of the side is equal. Okay. And after this, sometimes we may get some important finds per unit primary resistance drop, per unit resistance drop, per unit resistance drop. Okay, so if you can consider per unit primary resistance drop, primary resistance drop. So this is the voltage drop by per unit voltage V1 or E1. So better to take EMF E1 I1 R1 by E1. Okay, same per unit secondary resistance drop, secondary side I2 R2 by secondary side EMF E2. Okay, in the same way, in slides completed. So let us take in this slide 2 points only there. Total per unit resistance on primary side is equal to I1 R01 by E1. Okay, total per unit resistance. Total per unit resistance on primary side is nothing but I1 R01 by E1. In the same way, total per unit resistance on secondary side. Secondary side in the sense I2 R02 by E2. I2 R02 by E2. Okay. So from this one, we can also say that the per unit resistance drop on primary and secondary is always equal. So we can consider as equal. So per unit resistance drops are equal on both primary and secondary side. Okay. So we can also consider percentage resistance as per unit resistance. Per unit resistance. Okay. After this, we need to discuss the very important thing in the transformer, that is losses in the transformer. Losses in the transformer. Especially you can say iron losses and copper losses. In the iron losses, we know very well, we have hysteresis and eddy current losses. So at least we may get 1 or 2 questions in the losses topic. Okay, losses topic. If the transformer is the total weightage is 5 marks, if it is a 5 marks, nearly 2 questions from losses only. Okay, 2 questions from losses only. So losses is that much of important. We will discuss the losses in the next session. Okay, in the next session. Okay, students. So in this session, we have completed the 2 important points: resistance transfer primary to secondary, and the vector diagrams of no load and lagging and leading cases, and this IW and IMU. Okay, IW and IMU. Okay, students, if you want to get PDF, visit suneelengineeringacademy.com. In that you have the video how to download the PDF. Okay, so that is the 1 minute video. Watch that 1 minute video, then you will get the idea how to download the PDF. Okay, so just to open the browser here, search with suneelengineeringacademy.com. In this you have the first video, that is how to download the PDF. Watch this 1 minute video, then you will get the idea how to download the PDF. Okay. Okay, students, I am going to end the session. All of you, thank you so much for watching, and all of you try to share this to all your friends. Okay.